Hi, I am Paul. This year, the DEE task group did some work about IOPMP. In April, Security Forum, we mentioned the main structure of an IOPMP. In June's World Conference, we discussed how to place IOPMPs in a platform. And now, we are going to move to the next subject, how to protect IOPMPs. I'm working for Andy's Technology and now focus on the platform security. This is my biography. Today's talks will be split into 5 parts. Firstly, I will briefly explain what is IOPMP for. Then, we will quickly review the major IOPMP models. The third and fourth parts are our focus today, protecting IOPMPs. At the end of the talk, we will have some concluding remarks. Let's see what an IOPMP can serve in terms of security platform. In case that you are the first time to the IOPMP topic, here we will quickly explain why we need IOPMP. This figure demonstrates a platform without an IOPMP. Every transaction issued from the RISC-V hard will be checked by its PMP. In other words, the PMP is the checker of such a transaction. However, whatever transaction is issued from another busmaster, for example, the DMA, the transaction will not be checked by any so-called checker. Then, an apparent attacker can utilize such a DMA to access any data it wants. Someone may say, all DMA operations should be checked by a security monitor before being performed. Such a pure software solution does solve a part of the problems. However, it might bring new risks. While you add more DMA-like devices into the system, the footprint of the security monitor increases correspondingly. It implies it makes attack surface broader. If your system has GPU, NPU, or other accelerators, the situation becomes more complicated because such a busmaster can get a piece of program as an input. Analyze if a piece of program will send an illegal transaction is not practical. Thus, the IOPMP was proposed. It's a hardware checker for all busmasters. We put IOPMPs in every path that transaction may go through to ensure no memory violation. Before entering our major subject, let's quickly review the IOPMP main structure and its models. It helps us to figure out which components we should protect. For an IOPMP able to check whether a transaction is legal, several pieces of information are needed. When a transaction arrives at an IOPMP, we should know which busmaster sent the transaction, then the memory region the transaction operates, and the direction of the transaction, read or write. The source ID here refers to the busmaster issuing the transaction. Each busmaster needs such an ID, which is used to represent a security identity in a IOPMP's scope. It doesn't have to be unique. If a group of busmasters has the same permission in every memory region, they can use the same source ID. In addition, some busmasters may play different roles, such as multi-channel DMA, a processor with multiple modes, or a processor running multiple virtual machines. In such a case, we should use different source ID to distinguish the real source. Just like PMP, IOPMP has ordered list of entries. Every entry has a memory region and its permission. The entry with lower index has higher priority. Any transaction crossing the region boundary is considered illegal. Then the major difference from the PMP is that IOPMP has up to 2 mapping tables which maps from a source ID to its entries. And IOPMP has 1 master port, 1 slave port, and 1 control port. The master port is where a transaction flows into an IOPMP. The slave port is where a transaction flows out an IOPMP after the check. The control port is used to program the setting of an IOPMP. This port usually connects to an MMIO bus. Besides, an IOPMP can act as a bus bridge crossing 2 types of bus, such as IOPMP2. There are 2 types of IOPMPs. The first type is the source enforcement IOPMP. This type of IOPMP serves only one busmaster. so it doesn't need a source ID. Thus, it has only IOPMP entries. No mapping is needed. The second type is destination enforcement IOPMP. This type handles multiple bus masters, so source ID are needed in such a system. There are more components to protect. Today, we will focus on this type. The current proposal is model-based. This is because we are not able to find a one-size solution to fit a variety of platforms. Thus, we provide several models. These figures demonstrate the full model is a superset of IOPMP components. When a transaction is issued from a bus master, it carries a source ID. The ID indicates who issued the transaction. By the ID mapping table, the IOPMP looks up the memory domain by the source ID when the transaction arrives. Since the table is encoded in the bitmap scheme, one source ID can associate with multiple memory domains. This means a bus master is allowed to access the region belonging to multiple physical function or device defined in individual memory domains. A memory domain has a group of IOPMP entries which are defined by the MDCFG table. We can retrieve relevant entries from the IOPMP entry array. And finally, we can check the permission for the transaction from these entries. If a permission violation is caught, we can perform several following reactions. The full model is not designed to apply everywhere. We may have different design goals, such as area constraint, energy budgets, or latency requirements. Then we provide several ways to bypass one or two tables in order to reach different design goals. So we have models. Here we show another three major models. We may reduce the SRCMD table by letting the memory domain ID equal to the source ID, or we may replace the MDCFG table by a constant shifter. By this combination, we have the four models. Besides, we have a standoff flow to help software to identify which model is in use. Now we have reviewed the major component of IOPMP. Let's look into how to protect them. So why do we need to protect IOPMP? IOPMP is the one to regulate who can access which memory domain. If those rules are modified maliciously, all IOPMP-based protection collapse. Such an attack is just like making an IOPMP close its eyes. Then it can utilize an DMA to steal or tamper with sensitive data under a closed-eye IOPMP. When we mention protecting IOPMP, what do we mean? We have two requirements. The first requirement is in a system, we should be able to control who can control IOPMPs. IOPMP itself is used to control who can access which. Now we just need to replace the which by the IOPMP's control registers. Then we can naturally achieve this requirement. In our previous figure, all transactions to IOPMP control register have to go through IOPMP2, so IOPMP2 is a good one to take this responsibility. As to the answer of who is supposed to be a trust software such as a secure boot or security monitor, and it's usually predefined. As to the second requirement, we want to provide a mechanism to enforce some important rules unchangeable, even when the trusted software is compromised. It's similar to the per-entry log of PMP. Lock means before reset, the locked content is not changeable. A usage case is an anti-rollback counter stored inside a chip. It can be accessed only during the boot time. Afterward, any modification will be denied. If we can lock the rule to reject any write operation to the counter after boot time, then we can protect them even when the security monitor is compromised during the runtime. After a brief of two requirements, let's see how to achieve them. we still assume all the control paths to IOPMPs have to go through a specific IOPMP. In this figure, IOPMP2 is the one. It is also the bus bridge to the MMIO bus. That is, IOPMP2 can control which SID can control IOPMPs, include itself. This is a reference flow to control which SID can control the target IOPMP. We need to use two memory domains. Here are memory domain 1 and 2. MD1 is used to deny control operation to the target IOPMP, and MD2 allow these operations. Then let the SID of permitted bus master associated with MD2. In the meanwhile, that the rest SID associated with MD1. We use the previous platform as an example. Here we allow only the RISC-V code to control IOPMP1. Its source ID is 3. The page shows the settings. In the SID-MD table, only SID3 associated with MD2, which allowed access to the control register of IOPMP1. The other associated with MD1, which denied access. What if IOPMP2 is modified unwantedly? It could happen due to a bug or a attack. It could incidentally create an wanted control path. This figure demonstrates an attack that changed the mapping of SID2 in the SID-MD table. It makes SID2 associated with MD2 but not MD1. This change creates an unwanted control path. It's from non-RISC-V code to IOPMP1's control register. So the next question is how we prevent IOPMP2 from unwanted modification. How can we mitigate such attacks? Remember our second requirement? The sensitive data here is above setting that only RISC-V code is allowed to control IOPMP1. The main idea is used to another memory domain, MD0, containing two entries, entry 0 and entry 1. Entry 0 for denying any control to the SRCMD table. Entry 1 for denying access to the first 4 entries, include itself. Once MD0 is associated with every SID, no bus master can modify the SRCMD table until reset. This is because MD0 enforces this and MD1 enforces the former and itself unchangeable. Besides, it also enforces the entries of MD1 and 2 non-changeable, which we defined previously. Actually, we create a loop of denying. No one can reopen it until the reset. The loop of denying is equivalent to a hardware lock. We can extend the loop of denying to cover more sensitive data. The effect is equivalent to a hardware lock. This figure demonstrates the steps. Firstly, we need to prepare MD0 with 2 entries. One is to deny the region of controlling the SRC table. The other is to deny the region of the first 4 entries. The 4 entries should belong to the memory domain 0, 1, 2 respectively. Then we should well initial the SRCMD table, because we won't able to change it afterward. It's included setting which allow only SID3 to control IOPMP1. After all setting that every SID associated with MD0. Please note that the bus master that is programming IOPMP2 should be the last one to associate with MD0. This is RISC-V code in this example. After these steps, the desired statement is locked and the setting denies any further modification. If you want to remove this constraint, this denying setting that you want to remove also denies your remove. By far, we saw a method of creating a loop of denying to lock a memory region. It uses only the basic property of an IOPMP, and this property can satisfy our two requirements. If it's visible to your system, you don't need the other lock mechanism. However, for some cases, higher flexibility is wanted. To lock who can control IOPMP 1, the loop of denying also asks us to lock the whole SRC table at the same time. It's due to that we need to enforce every SID associated with MD0. However, the minimum grant that an IOPMP can control is 4 bytes. So we have to lock all bits of SRCMD register instead of just few desired bits of them. If you want to keep the partial programmability of the SRCMD table like this example, lock who can control IOPMP 1, but leave the other MDs associations programmable. We will quickly realize we are not able to lock only a few bits of those SRCMD registered by above method. So we need a fine-grained lock. Before talking about the fine-grained protection, let's look again at the component that we want to protect. We have SRC table, which used to describe MDs associated with a SID. It can be considered as a bit matrix of 2 dimensions, one for SID, the other for MD. Thus, we protect the table from 2 directions, the per SID protection and the per MD protection. The MD CFG table defines which IOPMP entry belong to a MD. The relation should be able to be locked. An IOPMP entry contains a region and a permission. This content should be also able to be locked. We will not mention the SID protection subsequently. Even though SID are very important for an IOPMP-based system, however, they don't belong to the IOPMP itself. Their protection involves busmaster's design. In the current stage, SID protection is implementation dependent. In many cases, it even can be hardwired. If it is not, allow the change only in the boot time unless you have the other protection mechanism. We will begin with the SRCMD table. An optional register MDMSK is used to indicate which MD's association can be changed. A 0 bit in the MD field of the register means that its corresponding MD's association is programmable for every source ID. Otherwise, they are read-only. MDMSK.L is used to lock this register. A reference flow is as follows. Build a memory domain M, then set or clear the bit M in all SRCMD registers according to if the source ID S is permitted to access the memory domain M. Then make all such bits read-only by setting the bit M in the MD field. Finally, we log MDMSK register by setting the L bit, which is the MSB of the MDMSK register. Practically, step 3 and 4 can be done together. In case that you don't implement this register, wire them to 0. Okay, it's time to get back to this example. Lock who can control IOPMP 1 but leave the other MD's association programmable. Similar to the loop of denying, we need 2 memory domains. MD0 to deny IOPMP 1's controls, and MD1 to allow them. Step 3 is the same as the previous method. Step 4 locks the association from all SIDs to MD0 and MD1. Here, we don't need extra memory domain plus 2 IOPMP entries that we did by the loop of denying. That is what we mentioned, partially lock which cannot done by the previous method. After we saw the per MD lock, let's change an angle and see the per SID lock. Every SRCMD register has a lock bit error. It's similar to the lock bit in an PMP entry. The difference is that besides the error bit, to program the MD field in a SRCMD register, we should also refer to the MDMSK as shown in the previous slides. The error bits are optional. If an IOPMP doesn't implement them, it should be wired to 0. The figure illustrates the both dimensions of the SRCMD table and how to lock them. When you want to lock the table horizontally, you can use the per SID locks. They are the error bits in each SRCMD register. When you want to lock them vertically, you can use the per MD lock. Those locks are grouped in the MDMSK register. This page comes to the protection of MD-CFG table. The field T in every MDM-CFG register points to the top entry of memory domain M. Modifying the field changes the belonging of IOPMP entries. An attacker can add or remove entries from a memory domain by manipulating its T field. Thus, we add an option register MDLCK to lock those T fields. Before we discuss it, that's CN situation. Let's consider a memory domain with unlocked T field. If attacked to modify its T, according to the definition, the belonging of IOPMP entry in the following memory domains changes. No matter if the latter memory domain is locked or not, it disobeys the definition to lock entries belonging because the later lock can be affected by previous unlocked T field. Consequently, we should put all locked T fields together and place them in the lowest order. Thus, we define MDLCK.F as the number of memory domains which lock T fields and require that the value should not be decreased when written. That is because decreasing the value means unlock is not acceptable. Besides, the error bit of MDLCK is used to lock this register. MDLCK is optional. We can achieve this by a loop of denying. However, using MDLCK is more convenient and saves some memory domain and IOPMP entries. When you want to incrementally lock belonging of IOPMP entries during different stages, MDLCK is even more convenient. The last one is the protection of individual IOPMP entries. Please recall, an IOPMP entry has priority. The lower order entry has higher priority. Thus, we should put locked entry in the lower position. Otherwise, an unlocked entry with higher priority can override locked entry with lower priority. It's implied that malicious manipulating an unlocked entry can weaken a locked entry. It's not what we expected. Thus, the locked entry should be placed together in the lower order position. We define the F field in MDMCFG as the number of locked entry for the memory domain M. Similar to MDLCK, the F field should be not decreased when written. Besides, error bit in a MDMCFG is used to lock the F field. We are close to the end. Before wrapping up, let's summarize this session. We explained why we need IOPMP to secure a platform. We find that the pure software solution cannot perfectly handle all kinds of situations. We also glanced at the major models in the current IOPMP proposal. Then we dive into how to protect IOPMP. We saw the loop of denying, which provides a coarse-grained protection, which doesn't require any new features. Finally, we look at several fine-grained protection mechanisms. Thank you for your attention. If you have any question about the presentation or want to participate in our IOPMP discussion, you may send them to the TEE task group or connect with Andy's Technology. Thank you very much.